The European Social Class for Molecule Research, CERN, is uncovering subtleties of one more molecule smasher today, something on various events more prominent and 2 times as critical. It has seen 3 new particles that could be useful to us in figuring out how our universe was envisioned and what its future looks like. Researchers at CERN have actually uncovered disclosures that turn how we interpret the universe on its head. Beneath the external layer of their profound tests lies a huge scope of particles and forces so peculiar they could be straight far away from expected segments to different perspectives, to particles that challenge the actual premise of reality. What jumbling insider facts are concealed inside these tests? Might we at any point bob into the universe of CERN and disentangle the bits of information that could reconsider our universe? The entrance to new perspectives, a wormhole, could hypothetically show up all of a sudden above, and the explanation would be the striking evaluations driven at CERN, home of the colossal Hadron Collider, LHC. The LHC is the world's most prominent and by and large solid molecule smasher, found close to Geneva, riding the line between Switzerland and France. There are privileged insights about this unusual alliance that the world doesn't have knowledge of, privileged insights that could, in fact, change the way we view physical science in the universe. CERN, the European Organization for Nuclear Research, operates this enormous, legitimate instrument. It extends in excess of 27 kilometers and sits deep underground. The primary function of the enormous Hadron Collider is to allow physicists to test the appraisals of various theories of particle material science. This includes the high-profile evaluation of the Standard Model of particle physics, which helps us understand the fundamental building blocks of the universe. At its core, the gigantic Hadron Collider works by speeding up protons to essentially the speed of light before smashing them together. These impacts produce a shower of new particles, which experts study to gain insights into the laws of nature. It was through such experiments that the Higgs boson, often referred to as the God particle, was discovered in 2012. This revelation confirmed how particles acquire mass and was a huge moment in nuclear physics. The tests conducted at the gigantic Hadron Collider are crucial for understanding qualities that happen under crazy circumstances, essentially indistinguishable from those shortly after the Big Bang. The data gathered can inform us more about how the universe began, evolved, and about the key constituents of matter. This makes the enormous Hadron Collider a player in potentially uncovering new pieces of reality, including understanding dark matter and the fundamental forces of nature. Such high-level experimentation at CERN doesn't come without worries. Some speculate about high-energy tests creating dark holes or exotic matter that could present dangers to Earth. However, CERN ensures that all safety measures are met and laid out. Experts closely monitor these evaluations, and theoretical models declare that any hazardous conditions are incredibly improbable. Through its constant assessment and disclosures, CERN helps us understand the universe better and demonstrates the great potential of human advancement and collaboration in seeking knowledge. The LHC is humankind's current marvel. The titanic Hadron Collider at CERN isn't just a staggering piece of technology, it is a wonder of modern science and engineering. Coordinated under the Swiss-French boundary, the epic collider runs through a tunnel 27 kilometers in width and is as deep as 175 meters underground. This makes it the largest particle collider on the planet and one of the main instruments in the field of particle physics. The development of the gigantic Hadron Collider is intended to handle evaluations of extraordinary scale. The head ring of the collider, housed in a tunnel with a width of 3.8 m, contains 2 intersecting parallel beam pipes. Each pipe accelerates protons in opposite directions, quickly propelling them with a series of superconducting magnets. These magnets are central for maintaining the proton's path, bending their course at speeds near the speed of light. Surrounding the beam pipes are layers of cooling systems that keep the temperature colder than space, necessary to keep the superconducting magnets at their intended operating temperature. The size of the gigantic Hadron Collider is also highlighted by its use of thousands of magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 meters long and weigh 35 tons each, demonstrating the colossal physical scale and imaginative ambition behind the collider. The essential job of the enormous Hadron Collider is to inspect the rudiments of the universe by seeing the smallest pieces of matter. By speeding up particles to nearly the speed of light and then colliding them, the Giant Hadron Collider allows physicists to study the resulting particles produced during these crashes. This process helps in testing and expanding our understanding of the standard model of particle physics, which is the current best description of the subatomic world. One of the key goals behind the gigantic Hadron Collider's experiments is to uncover the secrets of the Higgs boson. Its discovery at CERN in 2012 confirmed theories about how particles gain mass. The enormous Hadron Collider also explores other crucial particles and forces, hoping to resolve key questions such as the existence of dark matter and the nature of the universe shortly after the Big Bang. The gigantic Hadron Collider aims to confirm the existence of new particles that speculative physics predicts, but have not yet been observed. These studies are essential for potentially discovering new physics beyond the standard model, including supersymmetry and dimensions beyond the typical three-dimensional perspectives. The vision behind the gigantic Hadron Collider is not only to understand the universe's structure, but to foster global cooperation, with thousands of specialists from over 100 countries participating. The gigantic Hadron Collider is proof of worldwide support in the pursuit of knowledge. Its design and scale allow it to tackle the most serious questions in physics. Its purpose extends beyond basic scientific curiosity, aiming to shape how we interpret the universe and inspire global collaboration in science. Through this enormous and complex contraption, humankind continues to expand the limits of what is known and venture into the quantum domain. But how does the gigantic Hadron Collider really work? At the core of CERN's research facilities, the gigantic Hadron Collider serves as a powerful magnifying lens into the quantum domain, allowing researchers to observe and study the fundamental particles that make up everything known to humankind. The process of particle acceleration and collision at the gigantic Hadron Collider is a crucial method for testing the foundations of physics. Inside the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel inside tubes maintained at ultra-high vacuum, replicating the conditions of space. Superconducting electromagnets, chilled to temperatures colder than space, help steer and focus the beams at designated impact points along the tunnel. These beams collide, smashing particles with immense energy. The impacts produce a variety of subatomic particles, some of which are very unstable and exist only for fractions of a second. To identify and analyze the results of these collisions, the gigantic Hadron Collider is equipped with enormous detectors, ATLAS, CMS, ALICE, and LHCb, each designed for specific types of analysis. These detectors capture data about the particles, including their mass, charge, and energy. This information helps physicists test predictions of particle physics theories, including the Standard Model, and explore particles and forces that govern the universe. One of the most important discoveries at the gigantic Hadron Collider was the detection of the Higgs boson in 2012. This particle, sometimes referred to as the God particle, is critical because it provides evidence for the Higgs field, which is responsible for giving mass to key particles. The presence of the Higgs boson was predicted by the Standard Model, and its discovery was an incredible achievement, confirming long-established theoretical predictions. Beyond the Higgs boson, the gigantic Hadron Collider has also been instrumental in discovering a range of other particles. For example, the collider has provided evidence for the existence of pentaquarks and confirmed the presence of tetraquarks, particles made of 4 and 5 quarks, respectively, particles that had never been observed before. These discoveries expand our understanding of hadronic matter, which is matter made of quarks bound together by the strong force that holds atomic nuclei together. These revelations showcase the predictive power of the Standard Model and open new avenues of investigation in particle physics, offering insights into the behavior of matter under extreme conditions, such as those shortly after the Big Bang. Speculative dangers, such as strangelets or small black holes, have been subjects of public interest and scientific inquiry. Strangelets are a theoretical form of matter that is more stable than conventional matter. The theory suggests that strangelets could convert any matter they come into contact with into strange matter. The fear surrounding this theory is that if strangelets were created during particle collisions at the gigantic Hadron Collider, they could trigger a catastrophic chain reaction, converting all matter on Earth into strange matter. However, extensive research and safety evaluations conducted by CERN and the global scientific community have addressed these concerns. CERN's ongoing research and experiments continue to push the boundaries of scientific understanding and innovation. Despite the theoretical risks, which have been thoroughly assessed by the scientific community, the results from CERN offer a wealth of data that challenges our fundamental perceptions of the universe. The pursuit of answers to questions like the nature of dark matter, the expansion of the universe, and the unification of the fundamental forces is a driving force behind these experiments. These revelations could pave the way for groundbreaking discoveries in physics, leading to potential advances in fields ranging from energy generation to space exploration. In addition to their scientific contributions, the experiments conducted at CERN also play a critical role in fostering international collaboration. The facility serves as a beacon for global cooperation, with scientists, engineers, and researchers from all over the world coming together to work on projects that are too complex for any one nation to tackle alone. This spirit of collaboration extends beyond CERN's research facilities, as many of the technologies developed at the Collider have found applications in other industries, including medicine, computing, and telecommunications. One of the key elements of CERN's success is its emphasis on transparency and open scientific inquiry. The data gathered from the experiments conducted at the LHC is made available to the global research community, ensuring that progress is shared and that the scientific process remains as open and inclusive as possible. This open access to data has allowed for independent verification of results, further strengthening the credibility of the discoveries made at CERN. As the LHC continues to operate and refine its experiments, future upgrades and new experiments are on the horizon. CERN's vision extends far beyond the current state of research, with plans for future accelerators and detectors that will enable even deeper investigations into the mysteries of the universe. New technologies and innovations emerging from CERN could potentially revolutionize the way we approach scientific research, offering new tools and methods to explore the most fundamental questions of existence. The research at CERN also holds profound implications for our broader understanding of the universe. The discoveries made at the LHC have already expanded our knowledge of particle physics, providing insights into the origins of the universe, the forces that govern its evolution, and the fundamental nature of reality itself. Whether through the discovery of new particles, the testing of theoretical models, or the refinement of existing theories, CERN continues to shape the future of physics and contribute to our understanding of the cosmos. In the coming years, the LHC and the scientists who work at CERN will undoubtedly continue to tackle some of the most profound questions facing humanity. As we peer deeper into the fabric of the universe, we may uncover even more astonishing phenomena, each discovery a stepping stone toward a deeper and more complete understanding of the forces that shape the world around us. The legacy of CERN and its contributions to science will undoubtedly echo through the generations, guiding the pursuit of knowledge and inspiring future breakthroughs in physics.